I'd like to welcome everyone to the webinar series of the Cybersecurity and Information Systems Information Analysis Center, CSIAC. Today's presentation is entitled Certified Security by Design for the Internet of Things. My name is Steve Warzala, and I'm the CSIAC Outreach Manager. A couple of administrative notes before we begin. First, all phones have been muted except for the presenters. Questions may be asked at any time during the presentation by utilizing the chat function, and time permitting, your questions will be answered at the end of the presentation. I'd also like to take a moment to acknowledge and thank our sponsor, the Defense Technical Information Center, DTIC. The funding that DTIC provides enables CSIAC to conduct these webinars. It's my great pleasure to introduce our presenter for today's webinar, Dr. Shukai Chin. He's a professor at Syracuse University. Shukai, along with his colleague, Professor Susan Older, have devised Certified Security by Design, CSBD, to apply formal logic and tools to design and verify trustworthy systems. He's worked on numerous projects with the Air Force Research Laboratory, and they have utilized CSBD to assure missions in cyberspace. Prior to joining SU, Shukai was a senior engineer and a program manager at General Electric. I will now turn the presentation over to Professor Chin. Good afternoon, Shukai. The floor is now yours.
Thank you, Steve. Hi, everybody. This is Shukai, and welcome to this webinar. And I promise not to show you too much math, but hopefully we'll give you the overview. And Steve, thanks again, and for everybody at Quantarian and the CSIAC. All right, so let's get going. So the first thing I need to do is acknowledge the support for this work. That includes the National Science Foundation and Transforming Undergraduate Education in STEM. That's the TWOS program. Also CERCO, we were a contractor with them to the Air Force Research Laboratory on these contracts related to Assured by Design. Also, I'd like to acknowledge my co-author, Professor Susan Older, and colleague Patricia Lowney, who helped, as always, clarify our thinking. The typical disclaimer, these are my own views and not necessarily anyone else's, so I'm just speaking for myself. Okay, let's get started. So bottom line, what is certified security by design? And essentially it's this. It's formal verification, and by that I mean formal proofs, that if a command is authenticated and authorized, then it is executed. And if a command was executed, then it must have been authenticated and authorized. And I think many of you, if not all of you, will recognize that this is nothing more than complete mediation of command. And it's easy to say, it takes some doing to actually get it done, particularly the second one, that if something was executed, then it must necessarily have been authenticated and authorized. And that's what I call the get back to sleep at 3 a.m. in the morning property, because that basically is saying at least the design is constructed in a way such there's no backdoor. So some of you, if not all of you, might remember Roger Shell of Multics fame. And, you know, if we consider why things like security by design matter, particularly in this age where we're now terming this as the Internet of Things, you know, really the Internet of Things is turning into a global command and control and communication system. But there is no apparent or consistent security concept of operations. And, you know, Roger Shell, you know, you know, certainly in his papers in the late 70s, was already saying that things like do not trust security to technology unless that technology is demonstrably trustworthy. And the absence of demonstrated compromise is absolutely not a demonstration of security. In other words, absence of proof is not proof of absence. And so every day there are more and more stories about Jeeps getting hacked and various things on the Internet of Things getting compromised. So that's why certified security by design matters. The other thing that's important, and I want to present right up front here, is that typically when we talk about formal methods or mathematical logic, at least in computing, there's this notion that, an understandable notion that only PhDs can do this, or only, let's say, students from the top 10 universities in the world can do this. And our experience has been that with deliberate planning and experimentation and development, that undergraduates are capable of doing formal proofs and certified security by design. And I will tell you some of the details. But the bottom line here is that we have experimented not just on Syracuse University students, but through, for example, the Air Force Research Lab's Advanced Course in Engineering Cybersecurity Boot Camp, which started in 2003. We've had the opportunity to experiment and develop these methods on over 350 undergraduate level interns from over 50 U.S. universities and from the United Kingdom. Now, I'll take you back right up to the top of the slide. Our goal, too, besides doing formal proofs, an important goal is reproducing verification results is quick and easy for third parties. So what that really means is that it's not good enough for me to say, oh, I proved it. What's important is if you were my customer or you were the third party evaluator, that you could take my work and very quickly and easily reproduce my results, particularly all the proofs. Okay, so what I'm going to talk about today is this. I'm just going to show you a way, not the way, but one way academia or universities can educate the next generation of engineers capable of designing the next generation of trustworthy cyber-physical systems. So there are 7 parts of this talk, only 18 slides, and we'll start off with some history. We'll look at some of the requirements for the job. I'll briefly discuss the approach, go through and introduce an IoT example, and then we'll close up with lessons learned, what we're doing now, and conclusions, and then if there's time and interest, questions and comments. Okay, so let's just look at a little bit of history and how we got here despite our best intentions. And actually, before the webinar, Steve and I were trying to figure out how long we've known each other, and I think we're easily into 25 years, and we were reminiscing about what computing was like long ago. But I'll date myself by telling you that this chart starts in 1971 with the introduction of Intel's 4004 microprocessor, which had less than 4,000 transistors on it, and I think it was a 4-bit microprocessor. And I started as a freshman in computer engineering in 1971, and by the time I graduated in 75, the 8080 had just come out, and what we were seeing then was really the movement away from large mainframes like Multics, like the GE 635, 645, and then the emergence of minis and super minis, and then, as we all know, personal computers began to make their appearance at the end of the 70s and the early 80s. And that's actually a very interesting cusp. Because back when, for example, Multics was in operation and wide use, many of you know that security was a primary design concern, and was accounted for in the design of machines, or everything back then from the again the GE Honeywell machines, the IBM 360s, etc., and particularly the minis and the super minis. As well. Now, when personal computers began to appear, right, if those of you remember, that chip area was precious. You're still dealing with 10,000 or fewer transistors, and the deal was that the that they were still, chip area was still precious, and so you really, in order to stay in the commercial business, you needed to use as few transistors as possible and cram as much necessary functionality. But one of the basic design assumptions was personal computers, in fact, are personal, and that there was that basically PCs are physically isolated, and a very good operating assumption was physical isolation also meant process isolation. And so, given the expensive nature of transistors on chips in those days, unnecessary features were eliminated. And of course, when you're carrying around your own computer and there's physical protection, it was thought that security was unnecessary. Now, the rest we know is history, right? In parallel to the development of PCs was the development of networking, and we see in 1991 the World Wide Web was born. In 1995, NSFNet was transferred to commercial companies, and and then here we are in 2000, where now PCs with very little built-in protection are now networked. And so, the single user assumption on PCs was no longer an operationally sound assumption due to networking. And understandably, DoD went with commercial off-the-shelf hardware and software to contain costs. And so, if you look at the time from 1970 to 2000, I've been at Syracuse University since 1986 as a faculty member. I can tell you that security back then was not even thought of as a primary concern in what we teach our undergraduates. And so what we have from 1970 to 2000 is a generation and a half to forget how to design in security. And essentially it disappeared from just about every curriculum that I know of. And so the bottom line here is, gee, how do we expect mission assurance or assurance of anything that involves our cyber physical systems when engineers designing them really don't know secure design methods? All right, so again, from 70s, 80s, and 90s, it's just a stunning growth and technology, and the problem we face today from securing everything from our Nest thermostats to systems flying in space to everything in between. I think we can draw some lessons from the Microelectronics Revolution. And let me, those of you who participated in this know the story, but for those of you who don't, there's this wonderful paper written by Lynn Conway, and that's her picture here, Reminiscences of the VLSI Revolution, IEEE Solid State Circuits magazine in 2012. And so what Lynn Conway did was really solve the problem of how do you address concerns at multiple levels of abstraction, from algorithms down to layouts of transistors on chips, and create and put within reach and the grasp of regular BS educated engineers full custom VLSI. And what she her profound insight is really quoted here. And she said, this wasn't about engineering new things, it was about the engineering of new knowledge. My key idea was to sidestep tons of accumulated vestigial practices in system architecture, logic design, and circuit layout, and replace them with a coherent but minimalist set of methods. And as I'll show you in the next slide, she created basically, she used parameterization. And she picked one parameter, lambda, and I'll show you in the next slide what that really meant. But what she essentially did was come up with models that were, in some ways, experts viewed at the time as overly simplistic, but hung together across various levels of abstraction and were simple enough so that engineers and engineering students could go from algorithms to register transfer level designs, to logic designs, to finite state machine design, to, down to gate level design, and down to transistors, and cram that all into their heads and produce useful artifacts with computer-assisted design tools. I'll just say, as a brief digression, during the 70s, late 70s and early 80s, VLSI designers were very few and far between. And at one time, it was viewed as I think, a national crisis or a national concern that there were so few VLSI designers. In fact, I read in one of the early magazines, Lambda at the time, saying that there were fewer VLSI designers than there were NFL football players. Now, that was also, I might say, a self-serving remark on the part of VLSI designers, because I think they also wanted NFL football salaries too. Okay, but I digress. So the implications for us when we are looking at security are these. So what should we focus on in our methods? And I think they are these: simplifying and simplifications that enable what we mean by security to be described and preserved across multiple levels of abstraction. And that means coming up with mathematical methods and design examples with predictable results. Really focus on ideal behavior. And so what I mean by that is, for Lynn Conway, a transistor was a switch, on, off, conducting, non-conducting. But electrical engineers, we all know that transistors aren't just simple switches. They are amplifiers of varying quality. So for us in crypto operations, what we do many times, and the way we use crypto operations like cryptographic hash functions, are we assume no collisions. In other words, that hashes are one-to-one or isomorphic. And then the key thing is part C, is her use of parameterization for simplicity and time durability of tools and methods. And what made all of this practical were computer-aided design tools, and for us, it's computer-assisted reasoning tools. And again, this is a shout-out to a lot of the research that was done in the 1980s, funded by Star Wars at the time, but also which created many of the first and second generation theorem provers. Okay, just as a quick illustration, I'm not going to give you a lecture on circuit design, but lambda here refers to the minimum distance. And so I'm not sure you can see my cursor here, but if you look in the top left-hand corner, you'll see two squares with a black square in the middle. That's a via, or a hole cut, and then that's cut into silicon, and it's showing that, gee, the smallest hole you can make is a square whose edges are 2 lambda, and the smallest, and that has to be placed within a piece of active silicon that's at least 4 lambda wide. And so all of these, literally thousands of size constraints, Conway summarized just in terms of a parameter, lambda, and she basically picked the maximum minimum feature size. In other words, she looked at all of the minimum feature sizes, she picked the biggest one and said, that's what we'll parameterize around it. And then she also idealized transistor behavior to switch behavior, et cetera, and more importantly, had consistent interpretations linking models at multiple levels. So at the layout level, you have, here, if you can see my cursor, you'll see a pink horizontal line crossing a green rectangle. Where pink and green intersect, that's a transistor. And at a switch level, a transistor is nothing more than an on-off switch. And then on-off switches can be linked together to form basic gates like NAND gates, NOR gates. And once you have NAND gates and NOR gates, you have flip-flops, and once you have flip-flops, you have registers, and you also have arithmetic logic units. And then because typical transistors have three connections, gate, source, and drain, if you have 100,000 transistors, you're dealing with 300,000 connections, and the possibility of getting 300,000 things right manually is just about zero. So there are computers as aided design tools to help out. So this actually is a pretty good playbook for how it is we got the Internet of Things, which we're now moving back into full custom specialized designs that are now networked to save power and space and provide only the functionality needed. And again, I think this is a must read for anybody interested to see how the profession rose to a major challenge on mainstreaming what was thought to be, an impossible task of equipping engineers to design everything from algorithms, architectures, right down to transistors. Okay, so let's get back to the realm of security, and let's look at the requirements on us. And I think there's no better paper than Salzer and Schroeder's Protection of Information in Computer Systems. That's their 1975 paper. And basically what they said there was, gee, if we want security, we need complete mediation. So access to every object must be checked for authority, and we also have to identify the source of every request. And so the second block, shows a simple command and control scenario, and this actually is fairly typical. You have, in this case, a commander issuing a go command to an operator, and that might be Alice. Bob might be the operator, and based on his understanding of what the rules of engagement are, who he trusts, and the authorizations, under particular conditions, he'll say as operator, he'll send the launch command to an application, and then the application will activate. And so if we think about what we need there, particularly if you're Bob, if we're Bob, we need to understand and precisely state what it means for Bob to recognize the authority of Alice as commander, and then the policies that basically say, oh, when the commander has authority over go commands, and that if he receives a legitimate go command, he should issue a launch. And then, of course, the final line there in the block says, oh, and by the way, we'll use digital signatures for integrity. Okay. So if we look at our assurance requirements, if we're going to look at this similar to what we did in VLSI design, or just plain old engineering design, we need a calculus for justifying our conclusions. And in this case, justifying actions, accounting for authentication and authorization. We need computer-assisted reasoning tools, so that they're kind of like spreadsheets, so that other people can reproduce and check and verify assurance claims. Just like our switching theory and switching algebra for hardware design, we need algebraic models of idealized crypto operations. And then we have to incorporate all of this with transition systems and add to the description and verification of transition systems, account for authentication and authorization as parameters. Okay. This is an eye chart, and I'm not intending you to look at the actual formulas there, but a particular command and control calculus that we found to be useful is described in our book, Access Control, Security, and Trust: A Logical Approach. But what I want you to see here is that there are basically 13 core inference rules or definitions. And this is very plain vanilla. So for those of you who are semanticists, and I quickly add that I am just a knuckle-dragging engineer. My colleague, Susan Older, her PhD is in pure and applied logic from Carnegie Mellon. So she's the real semanticist. I'm just a happy user and benefactor of her knowledge. This is essentially what we would call a multi-agent propositional modal logic. So it's really the next step above propositional logic that's used in hardware design. And again, the focus is on actions or propositions and commands as propositions, who has authority over what, how that authority is delegated on what certifications or statements that are made by recognized authorities, what policies are, and what trust assumptions we're using. And as Steve mentioned in the beginning, you know, folks at AFRL have used this to describe things that they're interested in. And during a 10-year partnership Syracuse University had with JP Morgan Chase and their security operations, JP Morgan Chase used this calculus to describe their partner key management system that's part of the SWIFT protocol. So SWIFT, as you might know, is the Society for Worldwide Interbank Financial Telecommunications. So these are the protocols that commercial banks use to transfer, you know, north of $200 million per transaction. You know, in 2009, I think JP Morgan was transferring funds on the rate of $58 million a second. So these are the, you know, these are important protocols for them. In terms of our tools that that we use for our approach, we happen to use the Cambridge Higher Order Logic Hall 4 theorem prover. This was originally created for hardware verification. And again, the benefit of higher order logic is functions or parameters. So for example, for describing transition systems, we can use next state and output functions, and we can specify that those are parameters, and we can do our proofs over all next state functions and output functions. What we have done using Hall is something called definitional extension. The benefit of that is that these are conservative extensions to the theorem prover, so everything we've done preserves this logical soundness of the theorem prover. Hall has extensive libraries, you know, everything from operational semantics to the ARM architecture descriptions and verifications of the x86 things, and also of our access control logic. And it has been in use since 1987. So what we do here, and what's shown on the right-hand side of this block, is the command and control logic, which you'll see is an inference rule, you know, on the right. You know, like many inference rules, above the line are the assumptions and below the line are the conclusions. But on the left, you'll see a little turnstile. That's a signal that this is a theorem that's proved in Hall, and this accounts for the Kripke semantics, you know, M-I-O-I-O-S, where M is a Kripke structure, O-I and O-S are partial orders on integrity and security labels, and then satisfaction, basically, I won't define what that means here, but then the access control logic formulas are in the remainder of the theorem. And so what this amounts to, if you pardon me for saying this, this is the equivalent of logical pornography. There's nothing left to the imagination. Now, the bottom block basically is this, that we have created our libraries for the access control logic with users in mind as opposed to other logicians. And so this is much like you would find libraries of macro cells in, you know, semi-custom and custom VLSI CAD tools. So we basically support equational reasoning where possible, and then we have lots of templates and working examples. Okay, so what do we essentially do here? This top diagram shows this. So we might start with a signed message where, let's say, we've previously defined an algebraic type giving the message structure, and then we define an interpretation of that message structure and give its meaning in the access control logic. So when we talk about a digitally signed message, maybe its interpretation is Alice's key, you know, is signing a message that says the Blue Force commander says go. And then it may be that the Blue Force's operator, Bob in this case, you know, has at his disposal a security context which includes various signed and unsigned certificates that basically are jurisdiction statements. So in other words, the commanders can issue a go command, policy statement to say, oh, if you get a legitimate go command, then you should issue a launch command, and various trust assumptions on keys. So for example, that K Alice speaks for Alice or is Alice's key, or there is a key of a certificate authority that signs what amounts to a public key certificate giving Alice's key. And then, so this is deliberately written in the form of an inference rule, and basically says if Bob is able to, gets a K Alice says Blue Force commander says go, given the jurisdictions, policy, and trust assumptions, he is able to logically conclude that the Blue Force operator says launch. Oops, and I should say it's Carol, not Bob. Carol will issue her command that says, and sign it with her key, and says the Blue Force operator says launch. And so that would proceed out as a signed message. And so what we envision here and what we have is various Hall theorems justifying the actions based on the interpretation of messages, certificates, policies, and authorizations in our command and control logic. So what does it mean for us as an example of building in security from the start? So if you think of transition systems, many times transition systems are about how you move from one configuration to the next. So if we were dealing with hardware, and we were in my hardware design class, we talk about moving from state to state, except that now a configuration includes parameters for an authentication function, parameters that are security context, so that's here given by a list of certificates, then an input stream followed by the current state, and then my output stream. And so what we're talking about here is transition systems that have authentication and authorization accounted for in their basic structure, and thus transition relations that must account for using them. All right, now this is a bit of an eye chart too, but let me just show you what this is. So on the left, we can think of as an input stream. In this case, it's some principal operating in the role, issuing a command. You see that goes into a state which we'll call the fetch state. So this very much mimics a fetch and execute model of computing. And then what we have on the perimeter are notions of command. We just modeled command as, let's say, command 0, command 1. We have privileged commands and non-privileged commands. And then we have choices. So this is essentially a virtual machine monitor saying, oh, am I going to trap the command, or am I going to execute the command? And so we have our various trap states. We have our privileged state or execution states, PS0 through PSK, and our non-privileged execution states, NPS 0 through N. Of course, these are all parameterized by natural numbers, and this shows conveniently that these are infinite state machines, not just finite state machines. But if you look at this, and if you blow this up, I just want to show you one thing. These are the real Hall theorems, and what it basically says is, and I'll talk about executing a privileged command. It says that, gee, this transition relationship TR, given a for all crypt key structures that satisfy these relations, we will execute a privileged command. What? We'll move from one configuration to the next if and only if we've authenticated the input, we are using a defined interpretation of the configuration. So this is the mapping of or interpretation in the access control logic of the current state or configuration of our system, and if the command is authorized. And that would be a result of, essentially an inference rule or a theorem in the access control logic as implied by the interpretation of the configuration. And so notice that this is if and only if. So if I make the transition, then I know that I've been authenticated, I've been using a particular interpretation of my configuration, and executing the command is authorized. Also, it goes in the opposite direction. If the command is authorized, I'm using a particular interpretation, much like I would use, let's say, specify I'm using unsigned binary or 2's complement interpretations of bits, and then I've authenticated the input, then I'm going to make the transition. So again, those of you will recognize, and if you're familiar with Popek and Goldberg's 74 paper and Salzer and Schroeder's 75 paper, this essentially corresponds to segregating commands into privileged and non-privileged commands, having, let's say, user and supervisor modes, and then virtual machine monitors to decide whether you're trapping or executing, and in this case, discarding unauthenticated or commands. And again, if you can prove that all security sensitive instructions are privileged, then you know that this is virtualizable. Okay, and again, these theorems collectively show that a command is executed if and only if it's authenticated and authorized. And again, what's heartening about this is that there's a good deal of parameterization here, and that everything does fit on one page. Okay, enough of the math. Let's talk about the IoT example. And so, this is a very simple network thermostat, and I actually have to give credit to some of my colleagues who are looking at studying the smart electrical grid, security, privacy, regulation, and economics of smart electrical grids, and their focus on the security implications of having utilities take control over people and maybe even business thermostats during times of peak demand in order to moderate electricity demands during very hot months. Okay, so the operating scenario is this. Our thermostat is on the top right, and of course, the simple thermostats before networking would just have some sort of keyboard to display, physically isolated from any network, and the owner would basically have a full authority to do anything. However, once we add a network interface, we typically are dealing with a server, and the owner can interact with the server through their account on the server, and authenticate themselves with user ID and password. And then utilities will authenticate themselves through the server, or perhaps using public key certificates. And so, again, for authentication, owners use user IDs and passwords. Utilities use public key certificates. Authorization is done essentially by users or the owners of the thermostats granting authority to utilities to alter the temperature settings in their homes if certain safety conditions are met. Okay, and so again, bottom line from here is what we need to determine is whether we should execute or trap a command from the utility, and again, it's based on the principles of authority and the security sensitivity of the command. Okay, so this is about as simple as I can draw it. Again, what this is showing is in the ovals are the configuration of our thermostat. Enabled means the thermostat is the utility has been enabled or has been granted authority to change the temperature settings. Disabled means the utility does not have authority to change the temperature settings. N and K are natural numbers, and they are supposed to reflect the temperature setting in the thermostat. So essentially, the configuration of a thermostat is utility control enabled or disabled, and what is the actual temperature setting. And so for the owners can do anything they want, right? So they can basically execute a status command, which we'll see below is, just reports the state of the thermostat. In this case, it's enabled and it's set at N. They can execute a change the temperature setting from N to K, and they can also disable utility control. And again, that the owners can do anything. The transition diagram for a utility is this, that if the utility is enabled to change temperature settings, it can always execute get the status of a thermostat. But if the thermostat is disabled, any attempt to execute a privilege command, namely change the operating mode from disabled to enabled or enabled to disabled, or change the temperature setting, will be trapped. And so what we see below then is a simple summary that, our command classification is setting temperatures are privileged and security sensitive. Enabling utility or disabling utility control is privileged and security sensitive. Reporting status, in our view, is unprivileged and innocuous. And so again, this meets all the requirements for virtualization. So what we verify again in Hall for this particular example is commands are executed if and only if they are authenticated and authorized. Okay. To find out more, let me give a shout out to Tyson Brooks. About 2 years ago, he came up with the idea of producing a book on this book, Cyber Assurance for the Internet of Things. He was prescient and very wise to do so. And it's actually just came out from IEEE Press and Wiley, so it's available. The thermostat example is contained in Chapter 1 because Tyson was both wanted and was generous in terms of wanting the full details and accounting for all the details in the example. The description really takes the better part of 99 pages, but everything is there, and the appendices in Appendix C and D show all the thermostat theories as well as the access control logic theories. But more importantly than my work is that there are the 10 additional chapters, and the 10 additional chapters are from authors with additional viewpoints, and I can say that they are wonderful papers. If you want the full details on the Hall theories, we do have our NSF-sponsored textbook and lab manual, and there's the URL for that. If you really, really want the Hall source code, just email me and I can bundle it up and give it to you with instructions. Okay, so we've been at this for a while, primarily through AFRL and the ACE program. So what have we learned? So the C2 calculus seems to span multiple levels of abstraction. And let me say, I'm the first one to say that the inventor of a method or the developer of a method, anything he or she says about their method and its effectiveness should be taken with a grain of salt. So you can certainly talk to AFRL, and you can look at their papers, and you can look at papers from Glenn Benson and Sean Croston from JP Morgan and their description of their SWIFT protocol. The algebraic model of idealized crypto operations was essential. Again, we don't look at particular implementations of, let's say, AES or DES or SHA-1 or whatever. What we do is we have a very simple algebra that describes what amounts to switch level reasoning that people typically use with crypto operations. But that enables us to make our authentication arguments. I can't say enough about parameterization and time durability. A lot of our transition theorems, transition system theorems, use a fully parameterized authentication, authorization, next state, and output functions. And so that means the theorems that are proved are generally applicable to whatever transition system you have. Again, even to do the simplest proof and as an antidote for self-delusion, computer-assisted reasoning tools are essential. Again, we use Hall. There are other systems like Isabelle Hall, PVS, the French system, Coq. You can, I'm not arguing against or for any particular system, just that we happen to have used Hall for. And finally, people with functional programming skills, because functional programming is thinking declaratively, folks have an easier time learning. However, everything we've written does not presume prior experience with functional programming. It's pretty straightforward to pick up. Okay, so what are we doing now? We are working with AFRL on the as part of their Assured by Design program, where AFRL specifies a sample mission. We are working to continue to validate and develop CSPD, and in this particular instance, it's a real pleasure to be working with AIS and with Parsons. AIS doing the software development aimed at particular missions and demos, and Parsons doing the hardware development. The next two courses, CIS 487 and CS 400, this basically says, yes, we have routinized this in our undergraduate computer science and computer engineering programs, and so we teach this routinely. 487 is kind of the paper and pencil version, and then 400 you can think of as like a VLSI design course where we actually bring computer-assisted reasoning tools to bear. And note that we not only do we use the access control logic, but we do Hall proofs, and we integrate this with LaTeX, so that when the Hall proofs are updated and theorems, or the documentation is updated as well. And again, this produces results that are all reproducible by third parties. And then finally, we have launched the MS Cybersecurity program and 634 Assurance Foundations, which combines both 487 and 400 is a core course, but at the graduate level. All right. Let me end here by saying, I guess you can't get better by quoting Abraham Lincoln, right? And I think this is this for academics like me is, is important. It says, we have a responsibility for producing tomorrow's engineers, and that means if we want things to get better, it's my responsibility as an academic engineer to produce products, methods, and products in the forms of methods and students who are capable of designing secure systems. And so really it's our our job in academia to equip the next generation of builders with the capabilities and tools needed for a secure system design, where this must be a routine outcome, not a heroic one. So routine, just like we would have in hardware engineering. And these are there are, believe it or not, plenty of eager students who are wanting to do the right things and to know that they're doing them right. So that ends my briefing, and I'll turn it over to Steve for questions and comments.
Okay, well, thank you, Shukai. That's a very interesting presentation. I think the obviously the technology that you're working on is important, and the concept and the approach that you're taking, I think is very promising. I enjoyed the analogies you made with the going back to the VSL allied design period there, and where you noted that there was the shortage of engineers that were able to produce those designs. And so we kind of have the same situation currently. I mean, we're there's a great demand, need for cybersecurity, individuals with knowledge in that area, professionals that can work in that domain, and right now there's a great shortage in there. So the technology you're working on, and the education and training you're providing to this new generation of folks is going to be critical and vital to the national security of our country in the years to come. So I think that's awesome. And so I guess one of the questions that I do have is that kind of from an analogy perspective, everybody can kind of get in and drive a car, and you don't really need to know what's going on underneath the hood. So with the technology you're working on, how much does somebody have to know about what's happening under the hood? How much math, or what do they really need to know?
Steve, that's a great question. And one thing I forgot to include on the slides is this: so that everything we've delivered to NSF is a statement. Basically, the level of math you need is a sophomore, in other words, a second year undergraduate level knowledge of discrete mathematics. So that typically is set operations, relations, and a little bit of logic. It helps if you can, if the term structural induction isn't completely foreign, but that's about it. And that's that's part of that degree of knowledge, mathematical knowledge, is standard for computer science and computer engineering. Not perhaps for all electrical engineers or mechanical and aerospace engineers, but discrete mathematics is fairly straightforward. Am I answering your question?
Yes. No. That's exactly what I was trying to gauge. To see what level of expertise and knowledge that the students, the individuals using this would need to have. So whether somebody with a good foundation, as opposed to there's just this elite few that can comprehend and utilize this, but it sounds like folks get good foundational training in the areas you've defined. They will be able to utilize utilize the technology and help develop produce secure systems that are going to operate the way they're supposed to operate. So.
Right. I mean, I think I see. I'm particularly resonating with the notion of it can't be the elite, and it's not to say that elite. I'm not against people who know and deeply understand things. It's like, so for example, just about every computer science and computer engineering student knows a little bit about hardware design, in terms of gate level design. And they use digital design logic, but that's nothing more than propositional logic that's been highly specialized to a task at hand. And it seems simple to them. So the idea here is that you don't have to know everything about logic and math, but we as academic engineers have to provide people with just enough theory with enough tools to get the job done. And it may sound crazy, but in academia, that's kind of the opposite of what we're rewarded for at times, right? Many times we're rewarded for being, for being the only person that can dig a very narrow hole 10 miles deep, and nobody else can do it. But in this case, right, the needs of the, societal needs are quite different. You don't want to be the only person that knows how to do it. You want to produce things like vanilla ice cream that are versatile, that serve their purpose in a wide variety of situations.
That's awesome. Yeah, that's just awesome. So we've got some questions from our attendees, and this one actually comes from YouTube. We're streaming on YouTube now. That's a recent development for us, and So the individual enjoyed the presentation, and the question is, what can you do? What can we do until CSBD can replace the current mess? And are you interested in finding all the logic, arithmetic, and semantic faults in existing software suites, regardless of their size and heterogeneity?
Yeah, I very much appreciate and respect the caller for asking that question, because one thing you notice I did not say here was the correctness by construction. And so let me say this, I don't think it's certainly not my first choice to, for example, produce a verified C or C++ compiler. So for, what's interesting about the Internet of Things is many times these are small enough systems, that are highly specialized controllers that can be captured by a simple state machine description, right? So I'm not talking about, building, the next version of whatever Pentium chip or anything like that. So so transition system descriptions are shared by both hardware and software. And so I think, so then you say, well, so how do we avoid the problem of perhaps having different interpretations at the logic level or the requirements or specification level and what's actually implemented? So let me say this. So I can certainly give you a transition system description. Let's say even it is a finite state machine, but it incorporates my logical interpretation of, let's say, I'm in user mode or supervisor mode, or this pile of bits represents a public key certificate that I may have. And the key thing is that's my interpretation in this logic of what of the information I have. Now you transform this into another pile of bits, and maybe it's implemented by a field programmable gate array, or maybe it is implemented by, in some software. But the point is there is some structure. Either it's that structure is in software or it's in hardware. And again, if I were the hardware or software designer, I'd say, oh, here is my interpretation of the control structure that I am using. And it's given in the access control logic too. And then we can do a comparison. And we can say, oh, are we in fact comparing, do we in fact have the same, we've translated in a sense from one representation to another, but we want to preserve the same interpretation. And so this is essentially a page out of equivalence checking, which is quite well known and practiced routinely, and certainly in the hardware community. And that, of course, bypasses the the question of was the compiler or did I have the semantics of C right? I mean, because near as I can tell, there is not a comprehensive semantics for C, and I'm not proposing that we need to solve that one. Does that answer? I hope that answers or addresses the viewer's question.
Yeah, no, I think that was great. I think you took care of the question. So I have a question. Given this, the target, looking at the Internet of Things, appliances, these or small inexpensive devices. I mean, manufacturers are kind of driven by cost. They want to try to keep their costs down as much as possible. So I mean, how would this affect, to try and bake in the design? Is that going to dramatically raise the cost of these devices? Have you looked at that aspect of it at all?
So again, this is where I'll put my academic hat on. I don't want to presume to know what commercial companies or aerospace and defense companies, how they do their costing. But I will reflect a bit on it. So I used to be a chip designer. So in 1982, 83, those were the days where logic to layout verification was new. And and you and I know, Steve, that when we get awarded the contract from DoD, there is a hard deadline, critical design reviews, et cetera. And so I remember my management saying, you better release on time, you better tape out on time, you better tape out on time. And as soon as we shipped the tape, the next thing they said was, it better work right, it better work right, it better work right. So so it's I can't guarantee, so really, I think cost is kind of like is arbitrary in the sense that it depends on where you draw the boundaries. Back in my day, at the GE Electronics Laboratory, as a program manager, we could be a cowboy. I mean, nobody required me to even have design reviews, much less use any type of verification tools. But my team elected to do so because we knew we were going to be hit with the "it better work" question, and in fact, it did. And even though the tools were new then, I was very thankful that we had. So I guess if I'm looking at a quarter by quarter, I wouldn't anticipate that taking additional time, which will be measured in staff hours, would be I'd be any cheaper. On the other hand, in terms of fielding a system with fewer bugs in it or fewer flaws after it goes out the door, I think these methods prevent bugs from going out into deployed systems, which we all know is a huge, is several orders of magnitude more costly. When it's on the drawing board, I can just use my editor and erase a line or change a variable. Once it gets out into deployed hardware or software, you're looking at recalls and re-engineering, and that's just a massive cost.
Yes, I think you can kind of summarize that as you can pay me now or you can pay me later, and better to pay the cost up front. I think you're much farther ahead in the long run. So once again, Chukai, I think the work you're doing here is great, and it's of vital importance. Thank you for taking the time to share it with our audience today, and once again, just thank you for the work you're doing and spending some time with our audience today.
Well, you're very welcome, and I thank you for the opportunity. So have a good day, Steve, and I hope everybody else has a good day too.
Same to everyone out there. Okay, we'll see you next month. Bye-bye now.